So today we'll talk about supporting GPU computing, but the idea is to have a really sort of general overview and see where everybody stands. And so I would love, or we all would love to hear from you what your experiences are, and that potentially we can then come up with future topics that would be more in detail covering certain aspects of supporting GPUs. So we thought that the good first thing would be to do a quick introduction of what the GPUs are and how do they differ from a traditional CPU computing, just in case some people on the call are not that familiar with it. So really, when we're looking at a GPU, which I see, which we have sort of a schematic on the left side of a latest 8100 GPU from NVIDIA, and a CPU, which is in this case the AMD Milan 64 core. It's kind of hard to see, obviously, because I put some stuff over it, but what you notice is there is a lot of little things in here, which are many simple cores on the GPUs, which also then contributes to a very high compute density on the GPU as compared to the CPU cores, which you have over here, and then some sort of a interconnect that interconnects the CPUs in the case of the CPU layout there. So really the big difference there is that the GPUs, because they are so compute dense, they are optimized for parallel operations, but they are not very good in sort of more complex or logically complex codes. And so they cannot really operate standalone. We have to somewhat offload the computation onto the GPUs in order for them to work. And so they need to somewhat work in concert with the CPUs in order to get the performance that you can get. And speaking of performance, if you take a look at these numbers that I put out over here, essentially you have about on the A100 you have 108 streaming multiprocessors, as they call it, which each has 32 cores. So that gives us 3,456 cores. But then when you look on a CPU, we do have those 64 cores, but they have two double precision vectorized floating point units. So essentially, if you look at the raw performance in teraflops for double precision math, the CPUs are not really that different. Well, they are 4 times slower than a GPU, right? But it's not as big as sometimes you hear that the performance of GPU is 100 times more than a CPU. That usually indicates either that you end up using these specialized matrix units that are in the GPUs, which are optimized for machine learning, or that your CPU code is not running very optimal. Yeah? So I just want to make people aware of that it's not like GPUs are a silver bullet that will get magically your code running n times faster. They are more powerful in general than CPUs, but care has to be taken in order to get that performance. And so if you're now looking at how the codes are being executed on a GPU, when we have a GPU capable code, we're essentially running our program in a host on a CPU. We need to copy the data to the device, which is the GPU, in order for the data to be processed. And that oftentimes is a bottleneck because the pipe that connects the host to the device tends to be relatively slow. So that's something to be very aware of when you're programming for GPUs, is to try to minimize the host to device and back copies as much as possible. And then as our CPU program runs, then it launches these kernels, which are the calculations that run on the GPUs. And there is a special mapping in how this calculation or how the data are being processed on a GPU. And they are organized in the whole kernel is organized on a grid. The grid is then dividing into thread blocks and threads, which I'm kind of showing on another slide over here. So if you really think kind of from the single unit of execution, which is the thread, which would be the same case on a CPU or on a GPU. In GPU, they are organizing these thread blocks, and the blocks have to all compute the same type of operation at a given time. And then you can create one or multidimensional grids, which allows you essentially to map your problem that you're simulating onto the threads that are running on a GPU. Yeah? So kind of looking at it again from kind of the simplistic view from a simple thread, we're going to organizing the work to thread blocks to grids, and the grids then or the threads are in the thread blocks are then being mapped onto those streaming multiprocessors on the hardware of the GPU. So we get generally you get 32 threads per block, or that would be the most efficient mapping in order to use all the capability of the SM, and they all need to perform the same instructions. That is the core of the vectorization. Essentially, what the aspect of vectorization is valid on the CPUs as well, but the vector units on the CPUs are not as wide as on the GPUs. Yeah, so you have like 4 to 8 wide double precision vector units on the CPUs, and on the GPUs generally these SMs are 32 wide. Yeah, so from that we can really see that the GPUs are really good for high throughput floating point calculations. For example, linear algebra. So really good example is the deep learning, where the matrices tend to not to be very big, and so you can also map them onto this. You can essentially create instruction units inside of the silicon of the GPU to create this to do this matrix operation efficiently. That's also that's the so-called Tensor cores on the newest NVIDIA GPUs, and new AMD GPUs has something similar as well. They call it matrix units or something like that. And the more dense the problem is, the better. So essentially, the more continuously you can feed the data to the processing units, the more performant it's going to be. And so we really have plenty of HPC codes these days that have been ported to GPUs that are exhibiting these characteristics. And there are things that you can do even with the less regular codes. For example, I'm just having a point here. Branch applications are possible, but we have to be aware that since the SM needs to, all the threads need to do the same instructions at a given time. If you end up getting in a branch, the being conditioned like an if statement, right, in your code, then the SM needs to execute both of those parts of the branch if the branch happens to branch, in both directions on that particular set of data that the SM is executing. Yeah? So that might slow things down a little bit, obviously, because you have to, some of the threads are executing parts that might not be really needed, but that's just the way how the GPUs are designed. Right? So again, they are a little bit simpler with respect to the CPU logic, but they are more dense, so there is more processing power that they can provide. Now, I want to mention a few things about how the GPUs can be used, and then we will have the first set of discussion. So, kind of in my mind, at least, there are two ways how we can use GPUs. One of them is to not even know how to program for the GPUs, but use the programs that somebody else wrote. And in our experiences, most of the users these days fall into that category because there is fair amount of programs that have been ported to GPUs, right? And so really, what we see the most in our usage is that we see traditional HPC applications that have been ported to GPUs. We see a lot of machine learning because of the fitness of the GPUs to the processing of machine learning and AI. And so generally, this approach is not really different from using standard CPUs, with the difference that the users need to be aware how to request the GPU and how to make sure the program is running on the GPU. And the second part, writing your own code, is still sort of a thorny experience, in my opinion, mainly because we are basically still reliant on the vendor-specific standards, mostly NVIDIA's CUDA, which works well, but it's not really portable directly to other GPUs that are coming up. The programming standards are there, but they are still not complete, or they are not as used as they should be, or maybe they are not as flexible, who knows, but anyway, there is still something to be seen in the future from there. And then obviously you will need, a user as a programmer will need to learn these standards and change your code in order to utilize the GPU. Yeah, so that is definitely a bit of a trouble part. And so now we are ready to do our first question and answer section, so that we can kind of gather a little bit of a snapshot of what you guys know or think about GPUs, and what do we want to discuss in this regard. Yeah, so we have two questions on our, actually it's not a Zoom call, I'm sorry, it's a Menti poll. We ended up using Menti in the end. So please go to this link, answer those two questions, and you can also go then to a call document where we can put some additional question, or you can put additional answers to a few other questions we have in case you feel inclined to do so. Yeah. So I will give you a few minutes for that, and I will then switch to our result page here, and we will take a look at what are the results.
Yeah.
And
so
I will hand it off to Christina now, who's going to be moderating the discussion.
So if folks can fill out the first 2 questions on the Menti poll, that's what's going to drive discussion in this first section. But while people are doing that, so basically we want to get a sense of how people are offering GPUs and how much of your staff is supporting them. I wanted to open it up also if anyone has questions based on what the overview Martin gave about kind of generally what GPUs are good for or what kinds of programs are being used or so on. Any follow-up questions or comments, please put them in the chat and then we can go through. But that was a great overview, Martin, thank you. I think especially looking at like the difference between CPUs and GPUs and what GPUs are really good for, I think was really, that's super helpful. Okay. So yeah, any other?
I was very curious about this result because this is, I haven't used this particular visualization yet. So
yeah,
well, we kind of get an idea, I guess, here. I was hoping that the bars will be a little bit taller so we can get a better idea. But the bottom line is that we do see that there is most of the institutions have more limited capabilities of their staff to handle GPUs, which is kind of my experience as well.
Yeah, I wanted to circle back to the answer to the first question, if you're able to go back, Martin. So it looks like most of you are scheduling in the cluster, which I think, Martin, in a little bit, you're going to talk about some of the scheduling and support concerns, right? Okay, so I think after the next section of the presentation, we'll maybe ask for other people's feedback on how that works for you, having users access GPUs in the system that you have. There was one of the questions in the notes. Let me just look at that real quick. If anyone knows of other fields besides the ones that Martin mentioned, like deep learning, some molecular dynamics, a lot of like computational chemistry that have really gotten a lot of benefit out of GPUs, I think we'd love to hear them. So yeah, so I have a question from Stephen, which we'll get to in a minute, but any other questions or kind of general big picture questions about GPUs before we dive into the next section of this presentation and discussion.
Looks like
I think we'll have more discussion later about how people are supporting them. Yeah, Justin?
Looks like there's 2 that just popped in the chat.
Okay, so there's a question about the survey. When we get to training, Alistair.
Yes, Alistair, I guess I was meaning that the question here was meant more how much of your staff is capable of supporting GPUs. And for that, I mean, you can offer training yourself, but you can also have your staff to train themselves. So really, it's just how many people are familiar with usage of GPUs and they can offer the help to the users. That was, I guess, the meaning of that question.
Jana, did you want to chime in on that second question?
I was just going to mention for Stefan's question about can GPU architecture affect a result? We've seen that as well. Still doing some digging into, exactly what we're observing there. But yeah, I'd be interested to hear if other people have had that happen as well.
I would say this is very common, or slight numerical differences are very common in parallel computing in general, because the way how you keep, say, when you accumulate a result over multiple processors, there is always some truncation in the floating point, precision, and that the order of how you do the accumulation may affect that truncation. So as long as you kind of do, say, if you have, say, 100 processors and you accumulate from one processor to another consecutively, you will get still always predictable result. But these days, these algorithms, say, for accumulation are optimized in, say, a tree-like fashion, where in order to essentially get this done quicker. And so you are not guaranteed that the order of accumulation will be the same.
Yeah. So
So-
Martin, I think, can we actually go on to your next? So two things. I have a question for the chat that people can respond to in the chat as they like. But Martin, I think you could go ahead with your next set of slides because I feel like it deals with certain issues like this.
Yeah.
And then we can see what other questions people have in that.
Sure, let's
area.
do that.
Yeah.
So this was again just more a general overview. I was kind of thinking maybe somebody will want to say chime in their experience of using cloud versus say separate servers, but the majority of us are using scheduled clusters, which is pretty much what we're going to be talking about in the next section. So let's just move on to that, and hopefully we will have some more topics for discussion and your experiences in there. So kind of looking at it from the supporting the GPU application. So now we want to discuss in this section how we support users and their applications on the GPUs. And so kind of looking at our HPC style applications, to which I would basically bundle everything where people run in a scheduled fashion through job scripts. In my experience, at least on our place, we have a lot of chemistry, either molecular dynamics or quantum chemistry, and some engineering. There are some engineering programs like ANSYS that have GPU support. So those generally we would install directly onto the machine. But now there is definitely a trend to move these applications into containers. So we would like to see what others are doing with respect to hand installing binaries versus either hand installing containers or telling users to pull the containers themselves. And then, of course, once we get this, if we are serving these applications to users, we have to create some environment modules, and that is probably a relatively standard approach for everybody. And then, do we also support or provide some sample batch scripts for users so they can create their jobs based on some examples. And then the other style of applications that we see is the interactive applications, mainly machine learning, like Jupyter notebooks with various Python frameworks for machine learning. And some of the engineering applications like the ANSYS, some people like to use the GUI, GUIs to create their models and run them directly. And so now the question is, how do we schedule these? Do we run them through cluster, or do we offer separate servers? So in our previous poll, we've seen most of the people are scheduling. So then the next question when you schedule comes, do you offer them in sort of an interactive fashion? So people need to wait, till the GPUs become available so that an interactive job can start. And so that is something that we, for example, over here, we have a couple of GPUs that we have dedicated on this interactive queue, which is more accessible. And then the last question that I would have is, if we schedule it, how do we then offer the Jupyter notebooks? Do we have separate Jupyter Hub servers, or do we use open on demand? And open on demand, I'm presuming it's kind of starting to prevail because of the simplicity that it provides. Now, for the challenges that I see, and Asher, who's going to be our co-presenter, he's going to be telling a little bit more details about it once I end, is that how do we tell users, how to educate users how to ask for a GPU, because that can get a little bit more complicated than just the scheduling a normal CPU job. How do we get the program that works on a GPU? So either us or the users. So I've mentioned that in a previous slide. So either the binary container or some kind of a framework. And how do we ensure that the GPU is being used? It happens to us here and there that the user is running and they don't even realize the program's not using the GPU at all. Yeah? So do we actually go and analyze the GPU usage, or do we provide users some tools that allows them to see the usage for themselves so they can sort of self-police their execution? And then, so this would be kind of a basic support questions, and the more advanced questions are more related towards the programming and sort of getting the most performance out of the GPU. So one of them is, the main problem really in my mind is the programming aspect, that you have to essentially know the new programming approach in order to program these GPUs. You do have to be somewhat aware of a support person on how the GPU drivers and kernel modules interact with the libraries that are sitting above them. So compatibility of CUDA versus the drivers, for example, we get hit by that occasionally. And then sometimes the GPU generations come into play. So we might have a binary that has been optimized for certain compute capability, as NVIDIA calls it, which might not be the one that the user is trying to run the GPU on that GPU. So we somewhat need to educate users either to build the codes with wider GPU compute capabilities, or just can they figure out that how the program was being built in. And then the data transfers I mentioned earlier as well. That is an important aspect. And finally, single versus double precision. A lot of us are trying to be cost effective, and so we are not buying the high end, double precision data center Tesla GPUs, but we are buying the commodities, sort of more commodity gaming GPUs, which have comparable single precision performance as the data center GPUs, but they have much worse double precision. And so how do we actually educate our users to be aware that, yes, you can get good performance, but you have to make sure your code is actually supporting single precision. And so with that, I'm going to hand this over to Asher, who's from Clemson University, which has historically had fairly large GPU deployments. So they have a lot of experience in supporting the GPU over the last decade or so. So Asher, go ahead.
Yeah, thank you, Martin. I'm Asher. I work at Clemson as a HPC research facilitator. I've been in my role for about 3 years now. So just to give you a brief overview of the GPU landscape at Clemson, we have about 620 GPU nodes. A breakdown of the different GPU nodes are included in the slide. Our most recent addition to the cluster are 34 A100 nodes. Every node has about 2 GPUs, and the scheduler that we run is OpenPBS. And what we have is we educate users to specify if they want a GPU, and if they want a GPU, which model they want. And I think initially we did not have this kind of routing within PBS. So it was actually, we ran into issues with users getting multiple different types of GPUs at once, which ran into a whole lot of issues. So now we kind of make sure that they specify what GPU they want, and if they choose any, then it's on them kind of to figure out that if they request for multiple nodes, that they will get different types of GPUs possibly. But on the back end, I think we do try to prioritize that they all land on the same GPU. So they can specify which GPU they want through the GPU model flag through PBS resource selection. We also have 2 special DGX A100 machines. Initially, they were not part of the cluster, but this year we did integrate it into the cluster, and access is limited only through a special queue to it. But we are exploring how we can open it generally to general users on the cluster, so that they have an opportunity to use it as well. Martin, next slide, please. Okay, so in terms of software support, we've tried to figure out the best way to support, and in the end, it's just we cannot find a unified approach. So we do a little bit of everything. So we provide environment modules for CUDA Toolkit, CUDNN, and the latest NVIDIA HPC SDK, which also contains multiple versions of CUDA Toolkit, their own implementation of MPI and NCCL. And for some applications, for example, LAMPS, we do provide generic modules that users who are just starting out on the cluster can load and use. But we do have frequent users who want a custom installation or custom packages, and those we have a special documentation so that they can set them up themselves, or they can come meet with us during office hours and we could walk them through the process. We also support Singularity through NVIDIA's NGC. What I've not mentioned is also users can pull Docker images through Singularity and also run it on their compute nodes. We do support that. I think we do run into some issues if they want to run Singularity across multiple nodes. So we're still trying to figure out Singularity and multi-GPU support across multiple nodes. In recent, at least in the last year and a half, personally, I felt the number of users coming to us requesting for their own custom TensorFlow PyTorch installations has gone up a lot. And it's not only limited to computer science fields, but also we see them from mechanical, material science, chemistry, wildlife, and fisheries, and a variety of non-traditional HPC disciplines as well. I think from business as well, we have seen. So in those cases, what we usually find is the base library is TensorFlow or PyTorch, but they do want to use special packages which are only applicable to them. So in those cases, it does not usually make sense to install TensorFlow centrally, because TensorFlow can be a little temperamental and requires different versions for different packages. And also recently we found out that certain TensorFlow versions don't work with different AVX instruction sets. So depending on where they want to run their jobs, we work with them on creating their custom Anaconda virtual environment. Recently, we're trying to make a push for more virtual environments over Anaconda, because we found that Anaconda sometimes can mess with path variables in a user's environment. So then alternatively, as an interface to the cluster, we used to offer a Jupyter Hub interface where users could request GPUs and multiple nodes and run their, so they would install a kernel through their Anaconda virtual environment, and they would be able to use that environment on the Jupyter Hub interface. This year, we also introduced Open On Demand. And on Open On Demand, we have 3 interfaces. One is a normal, very basic Jupyter Lab interface. There's an advanced Jupyter Lab interface where users can customize what kind of resources they want. And we have another Jupyter Lab interface with a central TensorFlow kernel installed, so that if users want to just kind of test it out on the cluster and figure out or learn for themselves, they can load that particular interface. We also offer a VS Code server. We found that we have some users who are developing for GPUs and testing on the cluster, and they use the VS Code server to be able to use their codes. Next slide, please. So when dealing with users who come to us for their research issues, the main common 95% of the users, I would say, are users who are using someone else's applications or third-party open source or commercial packages. So they do not really understand the underlying architecture or hardware differences in a GPU. So whenever they come to us with memory issues, one of the most common things is, I requested for more RAM, but why am I still getting out of memory issues? And we have to explain to them, like, there are 2 separate memories over here in that they need to deal with, and that's a tough part for them to wrap their heads around. And one thing, and then we have to figure out, is this problem easily solvable if they could just move to a newer node with a newer GPU? Like if they were running on a K20, if they went on to P100, would that resolve the issue? If not, then it becomes very complicated, because then we have to look at their data and see if it can be broken out. And that's where your workflow or code refactor comes in. And piggybacking off, this is also running multi-GPU nodes, jobs across nodes. So a lot of users sometimes are very used to running MPI jobs on CPUs. So the -NP64 is quite common, and then suddenly find it does not translate as well to running multi-GPUs, where so those are some common issues we find. And also, I think PyTorch has a configuration script within the code itself to specify multi-nodes or multiple GPUs. So sometimes we do need to look more closely at their scripts to figure out if all of that has been set up properly. And there's also a lot of new emerging technologies, very fast developing landscapes. Sometimes we get users asking, do you support this? And sometimes I never even heard of where it came from. And then you have multiple libraries or packages built upon that are using their own implementations or interpretations on how efficiently to approach this GPU problem. And sometimes we are kind of blindsided by that. So some of it, for example, is OpenCL, Coco's OpenACC. I think OpenACC I recently had to deal with because WASP moved their entire code to using OpenACC so that they could support GPUs. OpenMP also does support offloading to GPUs for work. So, and all of them have different ways to approach this problem. So if we have to look at codes more closely, it can be a huge strain on our time. So we try to stay clear or offer an alternate solution if we come upon something quite sticky like this. One thing that's also an issue is if someone's running mainly on the GPU, our newer GPUs are on nodes where we have a very high CPU core count. So what happens is if they're running on a large data set and they have to copy from host to GPU memory multiple times, they could use up a lot of RAM and they could use up all the GPU, but that would then leave like 40 cores of CPU just unused on that node. And then the entire node would not be free for anyone else to run it. So this is something that we are trying to figure out how to balance resource usage so that these nodes are not wasted. See, next slide. Yeah, so that kind of wraps it up for me. If you have any questions, feel free.
Yeah. Thanks, Asher. Martin, you're muted.
I'm sorry, yeah. This wraps up the section on software support. And so we have a few more questions in Menti. So please go over and answer those. And I would really want to see more engagement now with respect to the questions. I see there is a bunch of questions. So I'll hand it off to Christina and we'll go over.
Thanks for the comments in the chat, especially the notes about GPUs being used for Oxford nanopore sequencing. That's new to me. So any notes that people can add to the call document about that would be great. I definitely would like to know a little more about what tools are being used and what it's good for. So I wanted to just call on a couple people. Stephen in the chat earlier, you mentioned using Jupyter Hub Open On Demand. Would you be willing to share like a little bit how that's gone for your center? Like what has worked well? Like what do users like about it? And what challenges have come up? If you'd be okay sharing for a minute.
Hello, can you hear me?
Yeah.
Okay. Yeah, sure. Let me see if I can get my camera working. But yeah, we recently at WashU just launched Open On Demand, and so it's relatively a new feature. But we do support GPUs, and it's been great. We haven't actually had much GPU engagement via Open On Demand. That's more still with the command line LSF submissions. But yeah, it makes it super easy. They can now we don't have options set up for like exclusive mode GPU resource requests, but yeah, I think it'll, as you know, more and more people learn about Open On Demand, and as we educate more people, I think it'll be pretty good for the community and pretty big.
Cool, thanks, Stephen. Alistair, you put quite a few notes in the chat about kind of how people interact with the system. Do you have any lessons learned for the group that you want to share?
Yeah, we set up a brand new NVIDIA DGX system a few months ago, and everyone was very excited. And we carved up some of the GPUs with MIG into various smaller chunks, and then they were completely ignored by the users in the cluster. So none of them want to use the MIG devices. They just want to use full A100s or even multiple A100s. However, what we have found is ideal. MIG is great for Open On Demand, where you can basically force the users to take what they can get. So you can provide them MIG slices via Open On Demand, which is quite useful. So I think that's my big takeaway right now.
Okay.
We're about to roll out a number of, we've got another DGX that we're going to be introducing soon, and then we've got about a large number I can't remember, it's about 80 A100s worth of Dell 4 A100 boxes that we're going to be deploying. So we're going to have a vast uptick in our GPU capabilities. So getting a handle on the tools and things to know how to monitor and report on the usage of these things, I think is going to be quite important to us.
Yeah.
I don't know what people use for reporting on jobs, GPU memory usage,
Yeah.
for example. That would be
Some good notes in the chat right now, actually.
Oh,
So
okay.
that's good.
Yeah,
Alistair, there's a
NV talk, I
follow-up
heard about that.
question for you from Eric. Do you know if people, or maybe Stephen, this is you as well. Do they want the 800 but don't need the entire GPU?
Very few people that we've had so far using our A100s have been using the full A100. Most of them request it and then they use a fraction of it, at least as far as we can tell.
Okay.
And of course, you get the inevitable small number of users who request it and never use it at all because they don't know what they're doing.
Okay. All right, sounds
They
good.
think it's magic. If you just request it, it will automatically convert your code to using the GPU.
Yeah, that's why Martin, I think the beginning of Martin's slides would almost be really useful for user training, which will be our last section, which we'll get to in a couple of minutes to help get across some of those ideas. I wanted to circle back. There was a question from Sean about using the cloud. So Sean, can you clarify kind of what issues you could maybe see being resolved by moving to the cloud? And then if there's anyone, there were a couple of people who said they provided GPUs by the cloud who want to share their experience and pros and cons. That would be awesome, I think.
Yeah, I can, I posted that somewhat in fun or sarcastically because, the cloud fixes everything. But I am kind of curious if anyone has feedback in regard to that. Does it fix everything? Does it fix the driver issues, the versioning issues, versioning between TensorFlow and, PyTorch and all of that? Or has people's experiences with various providers and say some pre-installed software packages kind of given the same experience that we all face, right? That it doesn't just, magic doesn't happen if you request a GPU, and magic doesn't happen just because you want some odd version of a library.
Right. Yeah. So anybody on the call, can you speak to using GPUs in the cloud? There's supposedly one or two of you.
Yeah, I'm afraid that nobody's gonna give us a silver bullet here either.
Well, the only comment I've got is we also have additional plans of provisioning GPUs from our own cloud, our private cloud. We're setting up an OpenStack instance configuration or cluster rather on our campus, and we'll be provisioning, our plans are to provision slices of A40 GPUs through NVIDIA's vGPU.
Oh, interesting. So OpenStack, right?
Yeah.
All right. Would be interesting to see if anyone has plans to do that with like VMware or OpenNebula or anything like that as well.
Yeah, this might be a good, we could have you report back, Alistair, how things go.
I'd love to. I mean,
for a future call.
It is a work in progress. So
Yeah.
we're not there. We don't even have access to the nodes of the GPUs on them yet. So we haven't been able to do any kind of testing.
Yeah.
So, but we're still getting to grips with OpenStack in general. So
Okay.
there's a long way. We're probably at least 6 months before we would have anything to talk about.
We do this via Hyper-V. So Hyper-V, you can do the same sort of pass through. OpenStack's typically KVM. So we've done it with OpenNebula like products too. That was iteration 1. It was a lot of handwork because OpenNebula, for instance, or Unraid is another one. They tend not to be very, very enterprise and management. So
yeah, I'm curious how the pass-through. This is obviously vGPU is different from pass-through because pass-through you're basically, I guess, passing a whole device through, but this is slicing and dicing.
All right, I'm gonna,
resources.
I want to make sure we get to the end of our talk today. Martin, can you go to the next Mentimeter slide? Just, okay, this is interesting, kind of the batch versus interactive. And so I asked a couple of people to share about interactive usage, but if other folks have any insights on I guess the pros and cons of those approaches that want to drop in the chat, that would be super useful. And Chris, I wanted to highlight your comment for the chat because yeah, I feel like we're in the same boat. Like for a while, it felt like we had GPUs and we definitely were trying to scale up with demand. And now it suddenly feels like there's been a bigger push in recent years. And if anyone else has had the same experience and just wants to concur in the chat, it'd be kind of good to know how many people are in that boat. Okay, I also want to talk about software installation, but I think training is also important. So Martin, if you want to switch back to the
Sure. I think what we will need to do
slides.
is to kind of gather some more feedback from you guys, what more detailed GPU topic you want to discuss. And so the software installations could be one, and the cloud, GPUs and the cloud could be one. So that's something definitely we can think of in the future and spend more time detailing these topics. Right, so let me switch gears here to my presentation again. Okay, so now our next part is the GPU training, and I'll hand it off again to Escher because they do much more than what we do over here at Utah. So he's gonna tell us what they do, and then we again want to get some feedback from you guys, what you guys do.
Yeah, so for our training, the only training that actively uses GPUs, not only, we offer a couple. So on the cluster itself, we run object detection with the TensorFlow API, which is just a basic how you request for a node, set it up, and then we have walked them through the entire process of end-to-end process of transferring data, cleaning their own data, setting it up, and then running the object detection module through TensorFlow. Before proceeding to this workshop, though, we do offer 2 preliminary workshops on machine learning and deep learning, where we introduce scikit-learn and Keras, but they are mainly run on the CPU rather than the GPU. And that sets up the users so that they're more easily able to follow through the object detection workshop. And through NVIDIA's DLI program, we actually have a couple of deep learning ambassadors. So they provide training on Rapids and Cura Python, but they do this on NVIDIA's own cloud through NGC. So students sign up for the workshop and they are provisioned with their own cloud resources to follow through the workshop. I've put a link to the ambassador program so that if anyone from your own institution would like to sign up with NVIDIA to offer that training, they could. And if you do sign up as, if you do get certified as an ambassador and you offer training, then NVIDIA will provision you with GPUs so that you can carry out the training. For software that use GPUs and to make sure that we have users know how to run those particular software on GPUs, we create example scripts that they could then use as to start up and then modify from there. Some of these examples come from us working with users who come to us and say, okay, how do I run this on the GPU? And then when working through it, we document it. And then at the end, we have our own example script that we can put in the documentation for other users to follow along. From time to time, we do have to update it because software gets updated and there are direction changes in software and they use different, they might decide to move to something else to move to run their code. So our documentation is public. We have all our examples and whatever we have worked with our users online. There are quite a few parts of it that might seem outdated, but I promise we are in the process of updating it all. So yeah, that's mainly how we offer training over here at Clemson for GPU usage.
All right, great. So we have only a little bit less than 10 minutes left. So let's quickly go over the last piece of the poll. And then we will, while we're doing that, we will open it up again for discussion about training options that you guys might be doing. So anybody who's got some specific interesting information about training, please let us know.
Yeah, while people are voting, we'd love to hear from anyone on your experience or training suggestions in the chat. Daniel, do you want to share a little bit about your experience?
I suppose if you'd like me to. Just an aside, perhaps most people, I'm not sure if anyone is familiar with the GPUhackathons.org program that's coordinated by NVIDIA, as well as many of the national labs are contribute as well as universities. But yeah, like regularly they offer hackathons that researchers can apply their codes for, in terms of partnering with NVIDIA experts as well as other GPU computing experts in the community to provide mentorship support, and as well as computing resources to accelerate the development towards GPU computing and the models. But if I imagine some of the people here might already be somewhat experts in this space. So if you also want to like apply as a mentor as part of those hackathons, you can look up the information the same on the GPUhackathons.org page. But it was successful for myself as well when our group recently used it for accelerating a flood inundation model on GPUs.
Cool. All right. Thank you very much. All right. So it sounds like most of us are offering kind of basic how to run GPU jobs on our cluster type training. That there's maybe more limited advanced curricula. Yeah, I'd again just encourage anyone to offer resources that exist, drop them in the chat. We'll move those over and save them in the call doc. And yeah, anyone else have GPU usage training war stories that they would be willing to share?
Hey, Christina.
Yeah.
I have one.
Go ahead,
I
Chris.
just need to chat about MATLAB. We just hosted a workshop for an hour and a half, 2 hours long. And the MATLAB instructors, normally they travel, but in COVID, they did it remotely. So we set up a room, we had about 30 participants, and they went through their training, and you could get an online account and follow along, or you could do it on our clusters. And then in spring, we're planning to do another one, which they offer, which is scaling up your MATLAB work to run on a cluster as opposed to a workstation. And they have a lot of the pretty advanced neural network programs, you know, of course, AlexNet, but really like 20 or 30 other ones, all the ResNet and Variety. So they are really scaled up to that. We have a campus ambassador who's a student, supports MATLAB. So we engage him to help out as well.
Cool. Yeah, thanks for sharing that, Chris. Jana, can I call on you to very briefly, if you're still with us, with your internet,
I'm still here.
share about what you're kind of what you guys do in terms of partnering with outside groups for training?
Yeah, absolutely. So like many of us, we have kind of low bandwidth. So we're always looking to optimize ways to provide training. NVIDIA has been helpful in providing training for specific applications. We work with them closely. You know, with vendors, it seems like you need to be a little bit on top of making sure that the slide deck isn't all just sales. The other thing that we've been moving towards is having them offer the training on our cluster so people can see exactly how to run it locally, as well as have materials then that we can propagate out that have example submission scripts and the rest that are appropriate for our cluster. Yeah, I think people are dropping from the call because they're like, oh, Jan is talking, that must mean we're done. But we're not quite done, right? There's a little bit more for this.
I think this is our last topic. I think the main thing that Martin has already said, so I'll let him do his final spiel, but we would love to know what we've covered today you want to hear more about in a future call. Do you want to talk about software? Do you want to talk about how people access GPUs? Do you want to talk about training? Please drop a note in the chat or put some notes in the Google Doc, and we will try to make that happen for a future call. So Martin, did you want to?
Yes, exactly. So
wrap up?
as Christina said, we want to continue this in the future in more details, but really the future, in my opinion, is going to get even more complicated than it is. So I want to give a few sort of bullet points here, what we can expect. The first is that AMD and Intel are both coming with GPUs, and you might have seen the news a few days ago that they have AMD their MI200 GPU now released, which is faster than NVIDIA. So I'm expecting it's going to get adopted more. So far, the AMD GPUs were not adopted that much because they were slower than NVIDIA. So people didn't really have the drive to do it, but now they will. So AMD is a little bit ahead of the curve right now. And Intel's coming up with their Aurora supercomputer that's supposed to be provisioned in the next few years at Argonne National Lab. It will be one of the biggest machines in the world. Two exaflop machine. Yeah. So it's supposed to be performant, but we haven't seen the numbers yet. So, but it will be definitely a different or more things for us to digest and adjust people's codes to. The other thing
exactly.
we should be looking at is that everybody is aware of the trouble of copying the data back and forth between the CPU and GPUs. So there are efforts to integrate these more together. So NVLink is sort of one of the approaches, right? But AMD has their own approach, and Intel for sure will have one as well. So we'll have to orient ourselves in that landscape. Apart from that, from the GPUs, there is all these other specialized
Martin,
CPUs.
we're at the top of the hour.
Yes.
Yep, sorry.
Anyway,
We have to call it.
You can see the rest over there. And thanks to everybody for coming.
Yes, thanks so much, Martin. And thanks so much, Asher. Really appreciated today's conversation. Before you drop off, just be aware of the research. The steering committee is always looking for volunteers. So we'd be happy to hear from you if you're interested in helping us out. Just email Justin Booth. He's at boothj@msu.edu. So one more time, this call was recorded. We'll be sending out an email with links to the recording. And thanks so much again for Martin Cuma, University of Utah, and Asher Antano from Clemson University. Our next call is going to be on December 9. We're having a party. Be sure and allot an extra 30 minutes. So it's a 90-minute call. It's going to be cross groups, and it should be awesome. So thanks to everybody who worked on the call: Justin, Gladys, Christina, Martin, Annalie, Katya, and I'm Jana Nugent. Thanks for joining us, everyone.
Thank you.
See you next month.
Thanks, Asher.
Thank you.